You think quantum mechanics sounds impossible. Good. That means you're already closer to understanding it than you think. Let me tell you something. Most people won't admit in the first 5 seconds. If quantum mechanics feels confusing, it's not because you're not smart enough. It's because nature doesn't care about your intuition. And neither do I. I'm Richard Feynman. I won a Nobel Prize for Physics, helped build the theory of quantum electrodynamics, and worked on some of the most important physics problems of the 20th century. But here's a lesser-known fact about me. For years, I felt just as lost as you probably do right now. I stared at equations that worked perfectly and still had no idea what they meant. That frustration nearly made me quit physics entirely. Nearly. So if you've ever thought everyone else seems to get this except me, stay right here. This video was made for you. And if you leave early, you'll miss the single idea that changes everything. Not just how you understand quantum mechanics, but how you learn anything difficult for the rest of your life.
People love to say quantum mechanics is mysterious. They whisper about particles being in 2 places at once, cats that are alive and dead, and reality collapsing when you look at it. They make it sound like magic. It isn't magic. It's stranger than that, and simpler.
In this video, I'm going to show you why quantum mechanics sounds impossible, why that feeling is actually useful, and why fighting the weirdness is the biggest mistake beginners make. You'll learn what quantum mechanics really says, stripped of jargon, stripped of fake clarity, and stripped of the lies people tell to sound smart. You'll learn why electrons don't behave like tiny billiard balls, why particles act like waves, and why measurement doesn't just reveal reality, it helps create it. You'll learn why even Albert Einstein, one of the greatest physics geniuses who ever lived, was deeply uncomfortable with what we discovered. And you'll learn why nature didn't care. When I was teaching physics at Caltech, some of the brightest students in the world came into my class convinced they understood quantum mechanics. By the end of the course, they realized they didn't. And that was progress. Confusion isn't failure. It's the beginning of real curiosity. That's why this channel exists. By the time this video ends, you won't have every answer. That would be dishonest, but you will have something far more valuable, a mental framework that actually works. You'll understand why quantum mechanics isn't about certainty, but probability. Why reality doesn't follow common sense. It follows math. And why that math, strange as it is, predicts the universe with absurd accuracy. I'll show you the core idea that reshaped physics, that particles don't travel along a single clean path. They explore every possible path, forward, backward, looping around, doing things that sound ridiculous until you calculate them and the calculation comes out right. Reality doesn't choose the most sensible path, it chooses the most likely one. And then there are my diagrams. Simple drawings, lines and squiggles on paper. People laughed at them at first. They thought they were childish. Those drawings ended up changing how physicists calculate the behavior of the universe. They turned nightmarishly complex equations into something you could actually work with. Physicists still use them today, decades later, because they work. You'll see why. But this video isn't just about quantum mechanics explained simply. It's about how to think like a physicist without pretending to understand things you don't. I'll tell you why I hated memorization, why I distrusted people who use big words to hide small ideas, and why I believe that if you can't explain something simply, you don't really understand it. The reason you must watch until the end. Near the end of this video, I'll give you the one sentence I used to tell my students, one sentence that shattered their expectations and freed them from the anxiety of not getting it. That sentence changes how you approach quantum mechanics forever. Miss it, and you'll still be fighting the subject instead of learning to live with it. Quantum mechanics doesn't ask you to believe. It asks you to calculate, to test, to stay curious, even when your intuition screams that something is wrong. And the universe keeps agreeing with the math over and over again. That's not philosophy, that's an experiment. So if you're curious, truly curious, if you want physics for beginners without being talked down to, if you want to understand why a Nobel Prize winning theory can still feel so uncomfortable, stay with me. I won't promise comfort, I'll promise honesty. Welcome to Feynman Flux. This channel is about curiosity, clarity, and learning without fear of confusion. If that excites you, even a little, subscribe now, we're just getting started. Your brain is fighting you right now. Not because you're incapable, but because it was never designed to understand atoms. Your brain evolved to dodge predators, throw spears, recognize faces, and not fall off cliffs. It evolved to deal with apples, rocks, and other people. It did not evolve to understand electrons that behave like waves or particles that don't have positions until you look at them. So when quantum mechanics feels wrong, uncomfortable, or even irritating, that resistance you feel is not failure, it's biology. I'm Richard Feynman, and I felt that resistance too. The difference is, I learned to enjoy it. As a child, I didn't grow up surrounded by scientists. My father wasn't a physicist. He sold uniforms. But he gave me something far more powerful than facts. He gave me curiosity. When we walked in the woods, he wouldn't tell me the name of a bird. He'd say, you can know the name in every language, but when you're finished, you'll know absolutely nothing about the bird. Then he'd ask how it flew, why it behaved the way it did, what made it different from other birds. That mindset shaped everything I did later in physics. I never cared much about looking smart. In fact, I distrusted it. I cared about understanding what was actually going on underneath the words. That's why quantum mechanics fascinated me instead of frightening me. It didn't pretend to be comfortable. It didn't care about my intuition. It just worked. Before quantum mechanics, physics was simple. At least it seemed that way. Newton's laws explained motion. You push something, it moves. Forces cause acceleration. Everything had a definite position and a definite speed. Classical physics worked beautifully for planets, cannonballs, and bridges. But when physicists started probing atoms, everything broke. Atoms refused to behave. Electrons didn't spiral neatly around nuclei the way planets orbit the sun. Light refused to choose whether it was a wave or a particle. Sometimes it interfered with itself like a wave. Other times, it hit detectors like tiny bullets. Classical physics failed at small scales, and no amount of patching could save it. That was the crisis quantum mechanics solved. Not by restoring common sense, but by abandoning it. One of the hardest things for beginners to accept is that quantum mechanics doesn't tell you exactly what will happen. It tells you what is likely to happen. Particles exist as probabilities, not certainties. Until you measure them, they don't have a single definite outcome. Reality itself becomes fuzzy. People hate that idea. They want the universe to behave politely. They want particles to have clear answers. But nature doesn't negotiate. Observation matters, measurement matters. The act of looking is part of the experiment, not a passive step at the end. It works better than anything we've ever invented. Quantum mechanics predicts experimental results to ridiculous precision, decimal places upon decimal places of agreement. We don't set like it, but the universe keeps saying, yes, that sets how I operate. When I was working on quantum electrodynamics, I struggled for years. Other physicists used heavy mathematics and formalism that felt opaque to me. I wanted to see what was happening. I wanted a way to think about quantum mechanics that was honest about its weirdness without burying it under symbols. That's where the path integral idea came from. Instead of asking what path does a particle take, I asked a different question. What if it takes all of them? Not metaphorically, literally. A particle doesn't choose a single path from point A to point B. It explores every possible path, straight lines, curved lines, wild loops, paths that go backward in time. Every path contributes something. Most of those contributions cancel each other out. A few reinforce one another. What remains is the outcome we observe. It sounds insane until you calculate it. Then it gives you the right answer. This idea didn't come from genius inspiration alone. It came from stubborn curiosity. I refused to accept explanations I couldn't make sense of. I refused fake simplicity, those neat-sounding stories people tell that fall apart the moment you ask a second question. I saw this problem constantly in education. Students memorize phrases like wave-particle duality or collapse of the wave function and thought they understood something. They didn't. They were repeating sounds. True understanding feels different. It feels uncomfortable. It feels unfinished. It comes with questions, not slogans. Confusion is a signal. It tells you that your brain is being stretched beyond familiar patterns. Pretending to understand shuts that process down. I'd much rather hear someone say, I don't get it, than watch them nod politely while learning nothing. Quantum mechanics forces honesty. You can't lean on everyday intuition. You have to accept probabilities, uncertainty, and mathematical structure as fundamental. That psychological shift, letting go of the need for certainty, is harder than any equation. And yet this strange theory powers the modern world. Lasers work because of quantum mechanics. So do transistors, which means computers, phones, and the internet. medical imaging, MRI machines, semiconductors, all born from principles that once sounded absurd.
My ideas are woven into all of it, often invisibly. Physicists still use Feynman diagrams, not because they're cute drawings, but because they capture how particles interact in a way that's calculable and honest. They don't lie about the complexity. They manage it.
If quantum mechanics feels unsettling, that's because it's asking you to upgrade how you think. Not just about physics, but about knowledge itself. It asks you to value curiosity over comfort, understanding over appearance, and questions over tidy answers. That mindset changed my life, and it can change how you learn anything difficult. If you've ever pretended to understand something just to avoid feeling stupid, you're not alone. I did it too until I realized it was the biggest obstacle there is. The moment you stop pretending is the moment real learning begins. Physics used to feel finished.
The rules worked. The equations behaved. You could predict the motion of planets centuries in advance and land a cannonball exactly where you wanted. For a while, it looked like nature had given up all her secrets.
Then the small things rebelled. Tiny particles, electrons, photons, atoms started breaking the rules, not bending them, breaking them completely. The very laws that explained the universe fell apart the moment physicists looked too closely. That was the problem that broke physics. I'm Richard Feynman, and I grew up right in the middle of that wreckage. People like to imagine that science advances smoothly, step by logical step. That's nonsense. Science lurches. It panics. It gets embarrassed. Classical physics worked perfectly until it didn't. And when it failed spectacularly. The electrons didn't move the way they were supposed to. They jumped between energy levels without traveling the space in between. Energy arrived in chunks, not smooth flows. Light behaved like a wave, one moment, and like a particle the next, depending on how you looked at it. The old rules couldn't explain any of it. That's when physics stopped being comfortable. I wasn't a traditional academic. I didn't act like one. I didn't think like one. I thought puzzles more than prestige. I took radios apart as a kid just to see how they worked. At Princeton, I annoyed professors by asking questions that sounded childish. But why does it work? What's really happening? Some people thought I was naive. Others thought I was dangerous. They were right about one thing. Curiosity is dangerous, especially when everyone else is pretending the problem is already solved. During World War II, I worked on the Manhattan Project at Los Alamos. We were building the atomic bomb, and the physics had to be right. There was no room for hand-waving. I learned something important there. Equations don't care about authority. They don't care who you are. They only care whether you're right. After the war, physics was still in crisis. Quantum mechanics existed, but it was clumsy. Quantum electrodynamics, the theory describing how light and matter interact, was a mess. Calculations exploded into infinities. Physicists could barely compute anything without getting nonsense answers. That bothered me a lot. I didn't believe nature was that ugly. I believed our way of thinking was the problem. Classical physics assumed the universe was deterministic. If you knew everything, the position and speed of every particle, you could predict the future exactly. Quantum mechanics shattered that idea. At the most fundamental level, nature doesn't give you certainties. It gives you probabilities. That was hard for people to swallow. They wanted the universe to behave like clockwork. Instead, it behaved like statistics. You don't predict what will happen. You predict the chances of what might happen. And when you run the experiment, the results always agree with those chances every time. Reality doesn't care about certainty. It cares about probability. That's not philosophy. That's its measurement. The trouble was that the math describing this behavior was unbearable. Pages and pages of symbols. Calculations so long that a small mistake ruined everything. Progress slowed. Physics needed a new way to think. I didn't set out to revolutionize anything. I just wanted to understand what was going on. One night, lying in bed, I started imagining particles not as rigid objects following strict paths, but as explorers. What if an electron didn't take one path, but all of them? Every possible path from start to finish. Straight paths, crooked paths, ridiculous paths. Each path contributes something. Most cancel out. A few add together. The result is what we observe. That idea became the path-integral formulation of quantum mechanics. From it came Feynman diagrams, simple drawings that showed how particles interact, lines meeting at points. Simple rules, Suddenly, calculations that once took years could be done in hours.
Physicists didn't have to drown in symbols anymore. They could see what was happening.
Quantum electrodynamics snapped into focus. The predictions matched experiments to astonishing precision. Eventually, that work earned me the Nobel Prize. But the prize was never the point. Clarity was. Feynman diagrams changed how science moved. They accelerated discovery. They spread through particle physics like wildfire. Even today, they're everywhere, in textbooks, research papers, and laboratories you've never seen. And yet, I never pretended I understood quantum mechanics in the way people expect. I said so publicly, loudly. I told students and colleagues the truth. Nobody truly understands it in a classical sense. That honesty mattered. When a professor admits confusion, students feel safe asking questions. Learning improves. Pretending to understand helps no one. I trusted questions more than answers. Questions mean your mind is alive. I watched students memorize definitions without comprehension, and it frustrated me. Intelligence isn't reciting formulas, it's curiosity plus effort. It's the willingness to sit with discomfort and not run away. Quantum mechanics rewards that patience, punishes shortcuts. If you try to force it into common sense, it fights back. If you let it be strange but precise, it reveals its power. The real lesson isn't just about physics, it's about thinking. The world is under no obligation to make sense to you. But if you're curious enough, honest enough, and stubborn enough, you can still learn how it works. And once you see that, you'll never look at reality the same way again. There's more to this story, much more, and the next part gets even stranger. Quantum mechanics feels like magic because it refuses to behave the way you expect reality to behave. It sounds unreal, it feels impossible, and yet it works perfectly, relentlessly, without exception. Every experiment agrees, every measurement lines up. The universe doesn't care that we find it strange. That's what first drew me in. I'm Richard Feynman, and I spent my life trying to explain why something so bizarre could be so accurate. Not by hiding the weirdness, not by dressing it up in mystery, but by looking straight at it and asking honest questions. People sometimes remember me as a physics genius, or as the guy who won a Nobel Prize, or as someone who worked on the Manhattan Project. But that's not who I was trying to be. I was a teacher, a storyteller, someone who believed, really believed, that anyone could learn physics if it was taught honestly. I didn't think physics was hard because people were bad at math. I thought it was hard because we lied to beginners. We pretended things made sense before they actually did. I refused to do that. The core rule of quantum mechanics is simple, even if it's uncomfortable. You cannot predict exact outcomes. You can only predict probabilities. That's not because we're ignorant. It's not because our instruments are bad. It's because that's how nature works. The universe doesn't roll dice because it's confused. It rolls dice because probability is built into reality itself. That idea shocked early scientists. It shocked Einstein. It shocked everyone. Classical physics promised certainty. Quantum mechanics took that promise away and replaced it with something better, accuracy. Then there's observation, measurement. The strange fact is that when you interact with a system, you change it. Particles respond to being measured, not because consciousness is magical, but because measurement is interaction. You don't peek at reality, you poke it. Reality responds to the questions you ask. That doesn't mean anything goes. It means the universe answers precisely every single time according to the rules. Those rules don't care about intuition. They care about experiments. When I tried to help students understand this, I avoided bad metaphors. Electrons aren't tiny balls. Waves aren't ripples in space like water. Those pictures help at first, and then they betray you. Instead, I used simple mental models. Think in interactions. Think in chances. Think about what can happen, not what must happen. Let go of everyday logic when it stops working. That's not giving up. That's adapting. And I want to be clear about something. Quantum mechanics is not mysticism. It's not magic thoughts creating reality. It's not spirituality hiding behind equations. I avoided those explanations because they're lazy. The math works. The experiments work. That's enough. You don't start need mystery when you have precision. If you're a beginner, here's how to learn quantum physics the right way. Accept confusion. It's not a flaw. It's a sign you're doing something new. Ask simple questions. The kind that sounds stupid to people who are pretending. Build intuition slowly, brick by brick. And most importantly, think like a curious human, not like a memorization machine. Think like Feynman. If this made physics feel less scary like the video, If you've ever felt confused and kept going anyway, comment below. I want to hear that. And if you're curious about how the universe actually works, subscribe to Feynman Flux. There's more to explore, more strange ideas, more honest thinking, and this channel is just getting started.